Now that we know how conformal transformations work, let's put them to use in a certain application. And the application we're going to look at is finding the eigenmodes of a curved waveguide. So this is a top view of a waveguide, which curves nicely like this. So this is the xy plane, and we're going to assume that in the direction perpendicular to xy, everything is constant. So we're interested in the eigenmodes of this particular geometry, which will also tell us something about the radiation loss that will occur in a system like this. Now, there's basically two approaches you could take. One is a more classical approach, and that's just saying, okay, what we have here, that's a job for cylindrical coordinates. So we're going to use a coordinate transformation to express this in cylindrical coordinates. So you could say that in this case, the geometry stays what it is, but we just use a more suitable coordinate system to express the equations. That, of course, will mean that the form of the equation will look very different. So Laplacian in Cartesian coordinates looks very different from a Laplacian in cylindrical coordinates, but that will give us an approach to find the eigenmodes in this particular case. Now, what we're going to do here is a completely different approach based on the technique of conformal transformation that we've seen before. So here, the idea is the following. We take a complex function, and we've seen before that this will keep the form of the equation intact. So after applying the conformal transformation, our Helmholtz equation will still look like a Helmholtz equation in Cartesian coordinates, but the price we pay for that is that the geometry, the distribution of the index profile will change. So in a way, these two approaches are the dual of each other. In this case, the geometry stays the same, but the equation changes. And in the second case, with the conformal transformation, it's in essence the other way around. Okay, so then the next question to solve is, what is the conformal transformation that we're going to use? Because we would like to start from this thing, which is a bit more complicated, and turn this into, for example, a straight waveguide, which we know how to solve. So can we think of a complex function that will take this curved path and transform it into a straight path? And people have proposed a solution to that problem in the 70s, where they have the following conformal transformation. W is f of z, and that's in essence the logarithm of z with some scaling factors here, and R2 is the outer radius of our band here. Okay, so this is what people proposed in the 70s. Question is, does this transformation indeed do what we expect it to do? Does it take a curved path and transform it into a straight path? Well, that's an interesting thing for you to work out for yourself. Pause the video and see that indeed this transformation does the job. And a useful approach would be to express this z here in polar coordinates, r exponential j theta. So do that and convince yourself that this takes this curved geometry and transforms it into a straight geometry. Okay, let's see what happens. So W is R2 times the logarithm of z, and z is going to be r exponential j theta. So then we divide by R2. And then we just make use of the properties of logarithm, which will turn products into sums. So let's group these guys together to say that this is going to be R2, the logarithm of R divided by R2. And then for the next vector, we have R2. And then we have the logarithm of the exponential. So they will happily annihilate to give us j theta. So what you see is that everything that relates to little r here is nicely grouped into the real parts of our complex number, and everything which relates to theta is grouped into the imaginary part. And that is indeed what we want, because if you have a certain path here, if you travel along this curve here, this means that r will stay the same, but theta will vary. And if you look at what that means in the transformed plane, if r stays the same and theta varies, that means that the real part stays the same and the imaginary part varies. And this indeed transforms into a line like this. So here we have it. We have found an equation that takes our curved geometry and straightens it out. So that's good news. The bad news is that there's a price we have to pay for that, and that price is that the refractive index profile gets multiplied by this transformation factor t, remember? So next step here is pause the video and calculate the transformation factor t based on the equations that we've seen before. So for the calculation of the transformation factor t, we need two ingredients. The first one is the partial derivative of u with respect to x. So this is going to be d dx, and then we take a look at u. So u, that's r2, the outer radius, times the logarithm of r. But since we need to take the derivative with respect to x, let's write down r as follows. And then we divide by r2. Okay, that looks like a job for the chain rule. So let's start. First of all, derivative of the logarithm. So then we just flip this thing on its head. So then we have x squared plus y squared. Okay, then we have a factor 1 over r2. And then we have to worry about taking the derivative of the square root. Is going to be 1 over 2 times that square root in the denominator, x squared plus y squared. And then finally needing to take the derivative of the argument of the square root. So that's going to be 2x. Okay. This 2 cancels, this r2 cancels. So finally we have that this is equal to r2 x divided by square root of x squared plus y squared. Okay, that's not too bad. Let's now do the same thing for v. So we need to calculate also the v dx. So this time we have the derivative with respect to x of, let's take a look. So, so that's going to be r2 times theta. So that's r2 times, and then theta, the angle, is given by the arctangent of y divided by x. So again, we need to express this in terms of x and y if we need to take the partial derivative with respect to x. Okay, so moving on, this becomes r2 1 over 1 plus the square of the argument. So that's y squared plus x squared. And then we need to take the derivative of 1 over x, so that's minus 1 divided by x squared. So this one becomes minus r2 y, that's the y, divided by x squared plus y squared. So now I notice that I've made a small mistake up here. So here we have the product of these two square roots. So the square root here has to go. Okay, so now we see clearly the symmetry between these two results here. And that's what we need if we want to finally evaluate the transformation factor t, because remember that's 1 over the square root of the partial derivative with respect to x of u squared, and then vx squared. So we need to take the square of what we calculated before, and then take the square root. Okay, if I can prevent this thing from jumping back and forth. So let's have a look. So this is going to be 1 over r2, and then we have 1 over, and then we have a huge square root here. So this is going to be an x squared plus a y squared for the numerators, and then for the denominators we have x squared plus y squared squared. Okay, so just evaluating this, if we flip this thing over, then we end up with something divided by the square root of that something. This is going to be just the square root of that something. So that's 1 over r2, and then we have the square root of x squared plus y squared. And remember, x squared plus y squared square root, that's just r divided by r2. But what we really would like to have is expressing this back in terms of u and v, because we will express the whole equation in terms of u and v. So that's the whole point of the conformal transformation. But that's pretty easy to do. Just remember the transformation. U was equal to R2, the logarithm of R divided by R2. So this means it's pretty straightforward here that U divided by R2 is the logarithm of R divided by R2. And the logarithm of R divided by R2, well, R divided by R2, that's exactly the transformation factor that we're after. So R divided by R2 being our sought after transformation factor is just going to be the exponential of U divided by R2. So there we have it. Finally, we know that the end result of the conformal transformation will be to take our original index profile and then transform that into a new index profile, which is the product of our original profile times our transformation factor, and that's just an exponential. So what this means is that if we start out from an index profile that looks like this, with just a core index and cladding indices which are lower, if we transform that using our logarithm, the price we pay for that is that the index profile gets multiplied by an exponential. So if I try to draw it, that looks something like this. So this is the z-plane and this is the w-plane. So the index profile gets skewed very much. So how does this help us? This means that solving the Helmholtz equation in our original situation is equal to a Helmholtz equation in Cartesian coordinates, but with this transformed index profile. So luckily we have lots of techniques available, numerical or approximate analytical techniques that deal with waveguides in the Cartesian coordinate system, and especially multi-layer waveguides. So what people typically do is they take this continuously varying index profile, and then they approximate that with a staircase profile like this, so that rather than having a continuously varying profile, you have just a large number of individual layers here. And depending on your required resolution, you take this step larger or smaller here. So you turn this continuous problem into a discrete problem, and then you go to your existing numerical package for solving the Helmholtz equation in a Cartesian coordinate system when you're dealing with waveguides which consist of multiple layers. And these things exist, that's a standard method, and then you can calculate what's going on here. Now, originally when this technique was proposed in the 70s, computational power was not so great of computers, so any analytical technique that could help you solve complicated problems was very welcome. Nowadays, the situation is rather different, but still this technique is very interesting, not only from a pedagogical point of view, but also because it allows you to give you certain insights into the physics of the problem. So what's going on with your waveguides here. So let's try and do that. So we know that a curved waveguide is equivalent to a straight waveguide with this funky index profile. So the question is, can you think about what would happen to the field in a structure like this? Knowing, of course, that light likes to be in regions with a high refractive index. That's the whole principle behind waveguides. So think about where in this waveguide the light would be. Would it be closer to the inner radius or to the outer radius? And can you also see in this case that light will tend to leak out of this waveguide eventually? So pause the video and think about these two problems. Well, pretty straightforward here, because the index over here is higher than the index over there. That means that light will tend to be clustered towards the outer band of your waveguide. But there's more going on, because the highest refractive index is not really here in the core, but is actually over there at infinity in the cladding. So depending on the exact shape of this profile here, how steep this is, you can see that something can go on, namely tunneling. So if this distance is small enough, then light will leak out from the outer radius of your waveguide and then run away into the cladding towards infinity. So here, visually, physically, you see the mechanism behind radiation loss in a band waveguide. Okay, so that's one nice piece of physical insight that we can get from this. Another thing that you can think about is what happens if I change my radius of curvature, if I change my R2, if I make it bigger or smaller, what will happen to the radiation loss? And can I understand what's happening based on diagrams like this? So again, pause and think about this. So one thing you could do is obviously making use of the fact that if R2 becomes very big, in the limits of infinitely large radius of curvature, then the curvature will be hardly noticeable and you will be back to a straight waveguide. And we know a straight waveguide does not have these radiation losses. So obviously what you expect from the physics of the problem is that if R2 increases, that then the bending loss will decrease. So that's the physics of the problem. Let's now have a look at the mathematics of the problem. So we know the transformation factor is exponential u divided by R2. So one very tempting argument could be that if you start from a certain transformation profile that looks like this, and if you increase R2, it basically means, because you divide by a larger number in the argument, that the exponential will not grow as quickly. So what this would mean is that if you increase the radius of curvature, then this thing here becomes less steep. And you might think, okay, since it becomes less steep, this thing will move away here. So there's something like this, and therefore the tunneling will be suppressed and the radiation loss goes down. That's a very tempting argument, but unfortunately it's not the whole picture. So pause to think about why this is not the whole picture, and especially think about the fact that in our transformation that we've introduced, this R2 was basically just a numerical parameter, right? So we could just as well have a transformation where f of z is just the logarithm of z. That would also have straightened the bend, but that would have resulted in a single t, which was independent of our radius of curvature r here. So what's going on here? What's really the story behind this, and why is this picture related to the steepness of the index profile in the cladding not complete? The answer to this conundrum is that there obviously is more going on than just what's happening with the steepness of the cladding index profile, because our transformation will do many more things. So if you look at the entire index profile, what will also change in addition to the steepness of this part here is, for example, the width of this waveguide. If you transform from the z-plane to the u-plane to the w-plane, this width will change depending on also the radius of curvature. So this is also something that will change. What will also change is the index here in the core, that can also change, varying depending on the radius of curvature. And all of these things together will determine how much leakage there is. So not just this thing in isolation, but also all of these other factors. And that means that a simplistic argument, just by looking at one of these factors, will not be able to give you the whole picture. And specifically in this case, where this thing keeps its steepness regardless of radius of curvature, and it's mainly going to be these other factors that will be able to explain why radius of curvature has an influence on radiation losses. But for that, you need the full picture and probably a numerical solution as well.